Let's continue our work with Introduction to Slope Fields. So you've heard in class that as we've gone through the course, we've often drawn curves and then we've picked a point of tangency and drawn a short tangent segment. So now we're going in the other direction. If you saw all of those short tangent segments, could you fit a curve onto that slope field? So think of each of these small segments as a brief tangent segment. So in question 1, first we want to use this slope field or direction field and find the curve that goes through the point 1, 0. So if we locate 1, 0, and then we follow the tangent curves to the best of our ability, and the closer we are, the closer the slope field is drawn, the easier this will be. Here the slopes are a bit far apart, so you might sometimes have trouble deciding which one to follow, but we want to make sure that we go all the way to the edge of the curve. So there's our solution curve that goes through 1, 0 for question A. That a capital A. Go right to the edge of the slope field. And now we want to find the solution curve that goes through the point 0, 1. So let's switch colors and find 0, 1. So we're using this point here, and we'll follow the curves as closely as we can. And looks like over here we get to the same curve up here. So there would be our solution curve that goes through 0, 1. And that was done in red. And let's choose another color for C. We want the curve that goes through -1, 0. So let's find this point, and we notice here that we have a linear solution. So these are easy to follow. And again, make sure that each of your curves, whenever you do this, goes all the way to the edge of the curve, edge of the slope field, but not beyond. All right, so that's a slope field, shows us all of the derivatives. So if we start with a differential equation and we don't know how to solve it, then we can at least sketch the slope segments. So once we have all these slope segments, then it represents all of the possible solutions. So there are many solutions, and we can see them from a slope field. So that's the value of doing this. Making the slope field at first can be a little bit tedious. What we need to do is simply plug in xy coordinates into the differential equation, and it tells us how to find the slope. So here it says for this derivative x over y, an example here, at the point 4, -2, we would put 4 in for the x coordinate and -2 in for the y coordinate, so dy dx would turn out to be a slope of -2. So find the point on your dot paper at 4, -2. So we're right here at 4, -2. And what we want to do there is plot a point that has a slope of -2. So this could be your target point. I'll erase this in a minute, but from this point, if we want a slope of -2, do you see how we draw the segment so that it would touch a target point using rise over run? So we could do that for every single point, so we've got a couple more here. If we use 0 for x coordinate and 3 for the y coordinate, look what happens when we use our formula. When we put 0 in for the x coordinate and 3 for the y, we would get 0, and that gives us an example of a pattern that's going to make this go a lot faster. So when x is 0 and y is not 0, so at the point 0, 3, we've got a slope of 0. And wouldn't that also be true for all x equal to 0? Where y is not equal to 0, then we'll get dy dx equal to 0. So when the numerator is 0, that means the x-coordinate is 0. So all the way up and down the axis here, we can put in these horizontal tangents. We have to be very careful to remember to skip the origin. So we know here that y cannot be equal to 0, since that would give us a 0 in the denominator of our derivative. Our next question suggests that we look at x is -2 and y is -2, and look what happens when we do the ratio of the x-coordinate to the y-coordinate. We'll get a slope of 1. So at -2, -2, our slope points with a slope tangent line with a slope of 1. So on this 45-degree line, would it be true that whenever x is equal to y, then we know that dy dx will be equal to +1. So all the way up and down this 45-degree, we can put in these tangent lines with a slope of +1. So the patterns that we find can make these slope fields go a lot faster. Does that suggest for you what happens if x is equal to the opposite of y? Then wouldn't the ratio be equal to -1? So on the opposite diagonal, we can do slopes of -1. So along this, and I don't know if my graph paper is squared up here. So here we should have, I'm having trouble on my tangents there. What else can we see as patterns? Well, let's think about another point like 2, 1. So dy dx at the point 2, 1, our formula is the x-coordinate over the y-coordinate. So here we would get a slope of +2. So again, look at that target point. So from this point right here to this point, that would be our target. So our slope of 2. And now let's think of the pattern. How could we make this go faster? Well, what happens at its mirror image? So what would happen if we chose the opposite value of x? Well, wouldn't we just get the opposite slope? So over here, our slope would be -2. So that can make your process go a little bit faster as you're filling in your slope field. So keep choosing some points. All right, so remember that we can have no slopes here. Y cannot be equal to 0. So remember not to have any slopes along that axis. And then if we just keep trying some points and finding the patterns, we can fill this in somewhat quickly. So for example, once you did the point 2, 1, you might also say, well, then I know what happens at 2, -1. At 2, -1, I'll have a slope of -2. As well. So our slope of -2 here, and then the mirror image over here of +2. So very quickly you can start doing some arithmetic and filling in these slopes. And I'm going to pause the video and finish up those slopes for you. Your question might be, how accurate do you need to be when you're drawing these slope fields? And you will never have to do this many points again on a slope field, so you might get a sample dot paper that has maybe 8 to 10 dots at most. If we wanted to have a really accurate slope field, we would use a calculator or a computer. Both of them can graph a slope field with the push of a button. All right, so our next question 4 asks us to put in one solution curve here at the point 0, 1. So the best you can do here, follow the slopes, and we'll come up with what looks like one branch of a hyperbola. And the important point here is you would not draw both branches. Your solution curves should be functions. So make sure that you keep your solution graph to the edge, but only one piece as much as will turn out to be a function. All right, so in question 5, you'll see a lot more work has been done to do a more complicated slope field equation. So if we look at how this chart has been made, so for example, if we choose x to be -2 and y to be +1, we would be substituting into this equation. Substitute the coordinates into your differential equation and come up with the slope of 4. So at the point -2, 1, so right here, the tangent line has been drawn with a slope of 4. So this slope field already given to you, but showing you how you could make these if you want to show your arithmetic in an XY chart. That might be a solution you might like. And now it's asked us to sketch the solution curve that passes through the origin. So follow the tangent lines to the best of your ability to the edge of the graph. And it looks like our solution curve here might be, for example, a cubic polynomial. All right, so match the slope fields to the differential equations, and now we can reverse the idea of those hints that we had a minute ago. So some ideas here are to look for the places where you would get horizontal tangents. So for example, if you wanted to work backwards from the graphs, I notice here that when y is equal to 2, our slopes turn out to be 0. So that you could look across and you could say, well, that narrows it down to A. If I put 2 in for y, I would definitely get a slope of 0. But that would also be true for B. If I put 2 in for y, I would get slopes of 0. So how would you choose between A and B? Well, let's think about that. You could use process of elimination, or you could say, look at A depends only on y. It has no x's in its formula at all. And the name for that is an autonomous differential equation. And what it tells you that as you go across the rows horizontally, you would have all the same slopes. Think, for example, if you put y equals 0. If you put y equals 0, then y prime would always equal 2. So as you go across the axis, do you have all of the same slope? So notice that that does not happen as we go across Roman numeral 1 graph. We do not have the same slopes horizontally. But if you look at graph number 3, when y is equal to 0, do you see that the slopes are 2 as we go all the way across? And when y is 2, did we get 0? So if you look horizontally as you go across graph 3, you can see that this graph is the one that is autonomous. So now we've matched letter A with Roman numeral 3. So I don't know which way you're going to write that. I'll write it both ways. So graph 3 pairs up with A. All right, so what do we know then? We've already looked a little bit at B. So you could say, well, I know that when y is equal to 2, we have to have horizontal tangents. And that rules out graph number 4. But we've already determined that 1 and 2 are both in the running. Oops, no, I guess graph 2 is not. When y is equal to 2, we do not have horizontal tangents. So I think that was enough for us to match that. Letter B pairs up with Roman numeral 1. So let's proceed then. What would we know when we looked at C? Here we could say, well, if x and y were opposites, whenever x and y are opposites, we'd get a slope of -1. So x and y are opposites on this 135-degree line. So along that 135-degree line, we should have slopes of -1. And if we look at our 2 graphs that we have left, I think that looks like it works on graph number 4, that on the 135-degree line, we've got slopes of -4. For letter D, when we're doing sine times sine, think of some simple examples. So if, for example, you put in 0, 0 at the origin, we know the sine of 0 is 0, and so at the origin we should have a slope of 0. Think of another simple point that we could put in here. If we put in pi over 2, which is about 1.5. So if we put pi over 2 in for both of those, then we should get a slope of 1. So here the slope should be 0, and here the slope should be 1. So you could look at about 1.5, and see whether you have a slope of positive 1. You could also look around the value of 3, because we know if we put pi in for either one of those values, that again we should have a slope of 0. So you could use that as a process of elimination. So you can see that that rules out letter 4. So when we're about 3, do you see any place where we have all slopes of 0? So if we're at about pi, do you see where here we do come up with 0 slopes? And vertically, when x is about pi, do you see that we all have 0 slopes there? So with a little bit of process of elimination, so I'm going to give 2, matching up with letter D. And as we thought before, for letter C, and we used our, when x and y are opposites, but you could choose some other points too. You could, for example, just pick a random point. You could say, what if I chose 4, 3? If I put 4 and 3 in here, I should have a slope of 6. So, oops, and that's, I guess, a little too large for our chart here. So let's try something simpler like 2, 2. If we put 2 and 2 in for x and y, we should have a slope of 3. So you can check some individual places also for your process of elimination. All right, proceeding. If all the slopes in a vertical column are equal, what that tells us is that the slope, the dy dx formula, depends only on x. So the y-coordinate doesn't seem to have any impact on it. So an example would be dy dx is equal to 5x squared plus 3x. So notice if you put 2 in for x, it doesn't matter what your y-coordinate is, you would have the same slopes all the way up and down a vertical column. All right, question 8, if the slope segments in a horizontal row are equal, what do you know about this? So a differential equation where that's true is called an autonomous differential equation, and what we know is that as we go across there, we would have all horizontal tangents. So an autonomous differential equation would give you a graph like the one that we saw in 3. So up above, the slope field here for Roman numeral 3 is autonomous. As you go across any horizontal row, do you see that we have all the same slopes? So that means that it depends only on y. All right, so if a horizontal line or a constant function is a solution, it is called an equilibrium solution. And think about when we talked about reaching the carry capacity in a logistic graph, that gave us an equilibrium solution. So it says, where does that occur in the graph at the right? So there are equilibrium solutions. You can see these horizontal solutions up here. I don't want to put arrows there. So equilibrium solutions where the tangent lines are 0. So that appears to happen at y equals 0, y equals 2, and y equals 4. And if we chose some solution curves, so if we said find the solution that goes through the point 0, 3, if you were doing the solution curve, look what happens. It sort of makes this parabolic shape. If we drew the solution curve through the point 1, 1, so do you see that we reach this? So it's sort of all of our curves sort of like going through the lanes in a swimming pool. So all of our waves would reach those barriers at the equilibrium solutions. All right, more with differential equations in our next assignment.